Hi, welcome back. We are beginning our study of magnetostatics with the Biot-Savart Law. So let us take a look at that. Now, before we get into it, I just want to point out that you'll see a lot of parallels or a lot of analogies between magnetostatics and electrostatics. And the better you can understand these analogies, the better it is for you to memorize these things and understand these things. So I'm going to point out these analogies or these parallel things that we can draw from electrostatics into magnetostatics as we go along. All right, so first of all, you want to be able to pronounce this thing correctly. I think these are two French guys, bio, so this is the T is silent there and the I sounds like E, so this is bio, and then the T is silent here, Savart, Biot-Savart Law. Now, similar to the electric field, which has units of volts per meter, the magnetic field, or the magnetic field intensity, has units, we're going to use capital H like that, has units amps per meter. So you know in circuit analysis that there are a lot of parallels to draw from volts into amps, volts to amps, the capacitor to the inductor. So here we are with electric field to magnetic field, and you already see a parallel thing here where the the voltage is changing to currents or amps. Now, here's the Biot-Savart law, and it looks intimidating at first until you get used to it. And the purpose of this video is just to understand the equation that I'm going to write down in a second. Given a wire that's carrying current I, so any current carrying wire creates a magnetic field. Okay, and let's say it has differential length dl. So we've got a wire with current I and a differential length dl. The Biot-Savart law finds the differential magnetic field a distance r away according to the following. So just a tiny magnetic field due to a tiny circuit element, wire element, is given like this. And based on what we know about unit vectors in the r direction, we could alternatively write this as I dl cross r over 4 pi r cubed, where r without the arrow is the magnitude of r with the arrow. Okay, so that's quite a bit there, actually. So let's try to understand this. First of all, let's write down some important points. Notice that the magnetic field is proportional to current. The magnetic field is proportional to current. Okay, and how do I know that? Well, I see I. Everything is multiplied by I. That means if you have zero current in your wire, then you have zero magnetic field due to that wire. If you increase it, and if you double it, then the magnetic field doubles. Triple it, the magnetic field triples. Everything that you would say about proportion here is true. And that makes sense. So the more current, the more magnetic field you have. That's pretty cool. All right. Also notice that the magnetic field is proportional to the sine of the angle between the wire and the field point. Is proportional to the sine of the angle between the wire and the field point. Okay, so how do I know that? I don't see any sign here in this equation. Well, remember the cross product? The cross product of dl with ar is the length of L times the length of the unit vector, which is 1, times the sine of the angle in between L and R and AR. So that's where the sine comes from. Another important point, the magnetic field diminishes or reduces as you get further away from the wire according to 1 over r squared. Okay, so we saw something similar to the electric force. So this thing diminishes further away from the wire as 1 over r squared. So the further away you get from that wire, the less intense or the lower the magnitude of the magnetic field intensity is. Now, most of this equation, most of this stuff here, the cross product, dl, ar, is trying to tell you what the direction of the magnetic field is due to this wire. And it's really the direction which is the crux of this law. This is the most important part. Of course, we can plug in numbers, but getting the direction is the key to understanding this equation. The direction of the magnetic field, this is what the equation is telling us, is normal to both the wire and the distance vector r, and then according to the right-hand rule, right? So the direction, I'll say that again, or I'll write it down, direction of the magnetic field is normal, perpendicular, to both the wire and the distance vector. According to the right-hand rule. I'm just going to abbreviate right-hand rule as RHL. And how do I know that? Well, I've got a cross product. So remember, the resultant vector from a cross product was a vector that was perpendicular to both the things that are being crossed. So if you cross the length of the wire with a unit vector pointing in the direction of the field point, then you get a vector that's perpendicular to both of them. So this is what we want to understand for the moment. And let me just draw a picture that maybe captures this a little bit better than the equation does. All right, here's our wire. It's a long wire. Of course, wires, we can't say, for practical purposes, we cannot say that a wire is infinitesimally small. But what we'll do is we'll take a point on the wire, maybe right here, and in the immediate vicinity, that little bit of chunk of wire is right there. It points that way. We're going to say current is moving that way. Okay, so here's my current carrying wire. Here's the current I, right? Actually, I'm going to erase that. I'm going to write that here. Okay, now let's say that we wanted to. So the claim is that piece of wire right there is giving off a magnetic field. In fact, every piece of wire is giving off a magnetic field. And let's say I want to determine the magnetic field, how about at this point right here? Okay, so that's the field point. And we'll call that point P. So what I can do is I can draw my radius vector, right? So this is r now in the equation, right? I'm going from the infinitesimally short piece of wire to the point in space in which I am interested. Okay, and now I'm going to look at the angle in between these guys. Call that alpha. And I need the angle in between them because I'm going to compute a cross product. And remember, there's a sine of the angle in between them that I need. Just to remind ourselves that the cross product of those two things would be the length of L, the length of dl, excuse me, times 1, because this thing has a unit length, times the sine of, in this case, alpha. Right? I've labeled alpha there. So for this field point shown in green here, in P, point P, the magnetic field is maximum versus alpha. So if I change alpha, if I change where I want the field point at, I'm going to get something smaller. Here is where it's maximum, since alpha is 90 degrees and sine has a maximum at 90 degrees. So any point lying on the green line will experience the maximum magnetic field with respect to alpha, right? So now let's determine the direction of the magnetic field at that point. So this is the right-hand rule, and I want you to do this with me. I'm doing this right now as we speak. With your right hand, point your thumb in the direction of L, okay, and then point your fingers. So no, excuse me. So point your fingers in the direction of L, and then curl them to the radius vector. So you're pointing up, then you're curling to the right, then your thumb should be pointing into the screen. So that means the magnetic field at this point goes in, and we represent in as an X, like an arrow that's going in. Okay, so again, that was, I point my fingers of my right hand up, then I have to kind of finagle my wrist and my elbow a little bit so that I can curl my fingers in the direction of alpha towards the field point. So that would be clockwise, and then my thumb is pointing into the page. Alternatively, what you can do, and ends up being the same thing, sometimes this is useful, you can point your thumb in the direction of the current, so the current is in blue, dl, and then your fingers curl in the direction of the magnetic field. So your fingers, if your thumb is pointing up, your fingers would be circling around the wire, and at this point, where the field point, your fingers would be going into the page. That's how we determine the direction of that magnetic field. Now suppose we looked at a different point. How about right here? Okay, let's call that point Q. And we wanted to know what is the magnetic field at Q, just due to this little piece of wire right there. Well, now dl, here's our radius vector now. dl and r are parallel. They lie on the same line, or it's actually 180 degrees, right? Well, the sine of 180 degrees is 0. So the magnetic field right here at this point Q is 0 due to this part of the wire. Now it's not 0 in general, because there are other pieces of the wire for which they are not parallel to this radius vector, but due to this piece of wire, the magnetic field at point Q is 0. All right. Now let's try to draw some more comparisons to what we know about electrostatics. So remember, with charge distributions in electrostatics, we could have linear charge distributions, surface charge distributions, and volume charge distributions. We're going to talk about different current distributions. So right now what we have is just kind of a linear idea, just current I, right? And so the what we can do is we can also have a sheet. We're going to talk about a surface, like a plate or a sheet, that carries current, maybe this way. So what we would talk about is how much, we call this K, how much current is passing through a line on that sheet at one point, right? At this point, how much current is passing through that line. And so what we could say is we talk about this K, and K would be in amps per meter, right? How much current through that line, how much current per line or per meter, right? So we would call this the surface current density. And then we can talk about current in a volume. And we've already kind of mentioned this previously in the course. Call that J, and we'll call that the volume current density. And be careful with the units here. That would be amps per square meter. So this is the volume current density. Even though it's per square meter, because you're talking about a volume has a slice of area. So how much current is going through that cross-sectional area. Over here with the surface current density, a surface has a slice that's a line, and so this is amps per meter. This is the surface current density. Okay, and this of course is just the current over here. So with that, let's suppose we wanted to know in this figure here, this first figure I drew with just the wire and the current I, let's say we wanted to know the total magnetic field, let's say at the green point, or it doesn't matter. But let's say we want to know the total magnetic field, and when I say total, I mean due to all of the little segments that make up the wire. How would we do that? Well, hopefully you guessed it. What we have to do is perform a line integral. We have to integrate across, or across the current carrying wire, the Biot-Savart law. Like that. Or if we have a surface current density, then we would have to integrate over the surface. Or if we have a volume current density, we would have to integrate over the volume. So I usually get a question at this point, do we really need to integrate this, or in practical applications, do you really integrate all this? Well, the answer to that is no. You don't really perform integrations in the real world, because the fact is that there are only so many situations where you can actually perform the integration, that there's an antiderivative. These simple shapes, as what we saw in electrostatics, where we had cylinders and spheres. The real world, we don't have simple shapes like this. So how do you calculate the magnetic field? And the answer to that is that you use a programming language. You actually do exactly what the integration is doing. You slice the thing up into very small segments, in a computer they can't be infinitely small, but you slice them up into into very fine segments, and then you run a loop, and the loop calculates over all of these segments the magnetic field, and then we add the magnetic fields up, and that's the total magnetic field. So that's what we would do in practice. But being able to do the integration for simple situations helps us with the understanding of actually what's going on. Speaking of the understanding, we're gonna look at a couple more videos on the Biot-Savart law and how we can actually do the calculations here using that DH equation. So I will see you in the next video. Thank you.